Welcome to Rome, the eternal city, and a living museum of civilizations past and present. The Pantheon, a temple dating back to Imperial Rome, is perhaps the most elegant and copied building in the world, and a structure with an astronomical connection. The Pantheon's dome is larger than St. Peter's, and in its center is an open oculus showing day and night. This temple, both open and enclosed, is an astronomical instrument, a type of solar quadrant. As the sun moves westward across the sky, the sun's light moves across the dome walls, like sunlight streaming through a porthole. The moving image tells both the time of day and the season of the year. The Pantheon was dedicated to the 7 planetary divinities: Jupiter, Saturn, Mercury, Venus, Mars, the Sun, and Moon, the 7 most important celestial objects in the ancient sky. The Pantheon's design required the collective wisdom of many ancient astronomers. We have sent reporters throughout the Mediterranean basin to identify and honor 7 of these amazing astronomers.
Welcome to Saqqara, home of the world's oldest major stone structure, and Egypt's first Great Pyramid. Imhotep constructed this step pyramid 5,000 years ago for King Djoser. Imhotep was an architect, high priest, physician, scribe, and astronomer, one of the few men of non-royal birth who became an Egyptian god. Saqqara is an immense cemetery for the ancient city of Memphis. The entire complex honors the dead and secures their passage into the afterlife. Imhotep designed the step pyramid to allow the deceased to mingle with the circumpolar stars that arc across the northern sky each night to link heaven and earth. Looking north, we can see how the pyramid captures the turning motion of the northern stars. As a scientist and priest, Imhotep would have predicted and monitored the flooding of the Nile. With its annual flood, the Nile River nourished Egypt for more than 5,000 years. Along its banks, ancient astronomer priests observed the turning star field from dusk to dawn. They were looking for a sign to predict the yearly Nile flood. Night after night, they studied the constellation of the Egyptian god Osiris, called Orion the Hunter by the Greeks. They followed its 3 stars in a row down toward the eastern horizon, lit by the glow of dawn. Each day, Orion would be a bit higher before dawn, allowing astronomer priests to see more stars below it in the pre-dawn sky. Finally, one morning, they saw the bright star Sirius for the first time. They realized that Sirius would be visible for the first time on the same day each year, just after the summer solstice. This day marked the beginning of a new year in the world's first solar calendar. The first sighting of Sirius also promised that a nourishing Nile flood would soon begin at the Egyptian capital of Memphis. Astronomer priests could count the number of days between the annual pre-dawn appearances of Sirius. Year after year, the counting continued until they were certain that the solar year is 365 and a quarter days long. More than 2,000 years ago, Julius Caesar visited Egypt and learned how to make a calendar with 365 days each year and an extra day added every 4 years. The resulting Julian calendar became the official calendar of Western civilization until the 16th century. For his discovery of the solar year and the use of astronomy to design pyramids and predict the Nile flood, we honor Imhotep, representing the Egyptian astronomer priest as our first amazing astronomer of antiquity.
Welcome to modern Tunis, site of ancient Carthage, and home of our second amazing astronomer, the Phoenician mariner. Phoenician sailors from the city of Tyre founded Carthage almost 3,000 years ago. Carthage soon became the commercial center of the Western Mediterranean, a position it retained until it was destroyed by Rome. With its capable merchant marine and naval fleet, Carthage controlled the passage between North Africa and the island of Sicily. But its sailors explored far beyond these waters. On the Temple of Baal Hammon in Carthage, there was an inscription which began, The voyage of Hanno, king of the Carthaginians, to the Libyan regions of the earth, beyond the Pillars of Hercules. The text goes on to describe Hanno's journey through the Strait of Gibraltar, known at the time as the Pillars of Hercules, and along the west coast of Africa around Cape Verde and perhaps to the equator. By day, Phoenician sailors navigated using landmarks along the coastline. By night, they became astronomers using the Phoenician star, also called the North Star in Ursa Minor, the constellation of the Little Bear. They knew that this star would always be in the northern sky, so they kept the North Star starboard to their right when they wanted to sail west. In contrast, if they wanted to sail eastward, they oriented their ship so that the North Star would be to their left on the port side. Other cultures gave the name Phoenike to the Ursa Minor constellation pattern. The voyages of Hanno illustrate how Phoenician navigators sailed around Africa, discovering distant settlements on the western coast of the continent. They may also have reached the British Isles. When they sailed north toward England, sailors would see the North Star rising over their bow. As they turned south, the North Star would be behind them and would sink lower in the sky as they neared the equator. For his skill in using the stars to explore new worlds, we recognize Hanno, representing all Phoenician mariners, as one of the amazing astronomers of antiquity.
Welcome to the modern Bibliotheca Alexandrina, a modern library and cultural center on the Mediterranean Sea at the mouth of the Nile River. This library was built on the site of the ancient Royal Library of Alexandria. At the time of Imperial Rome, this library was the largest in the world with an estimated 500,000 scrolls. The works of Aristarchus of Samos, our next amazing astronomer, were archived here. Aristarchus was the first scientist to explain both the Egyptian solar calendar and the role of the pole star in navigation. Aristarchus knew that the Earth was a sphere, a curved globe rather than a flat plane. Although his maps showed little beyond the lands surrounding the Mediterranean, he believed that his world was part of a giant turning globe. To understand Aristarchus's explanation, imagine we could observe the stars from inside the Earth, seeing the constellations through the ghosted continents. The pole star lies directly over the Earth's North Pole. Slowly, the Earth turns eastward, and we see that the Earth's North Pole does not move, and the pole star does not move either. We don't think of ourselves as moving, so let's stop the Earth and watch what happens to the stars. Now, how does this rotation look from the Earth's surface? As the Earth turns eastward, we do not feel ourselves moving, but observe the stars moving westward instead. The fixed stars seem to circle Polaris as the Earth turns under them. Facing eastward, we can see stars seeming to rise along the eastern horizon. Stars seem to set along the western horizon. The Earth's rotation also causes the moon and planets to move westward with the star field. This turning of the Earth also results in the sun rising in the east and setting in the west, bringing day and night to the planet. As impressive as this discovery was, Aristarchus offered another, more startling theory, one so radical that it would not be widely accepted for over 1,500 years. He explained the Egyptian solar calendar by proposing that the Earth circled the sun once a year, a moving Earth that not only rotated on its axis, but also revolved around the sun. Aristarchus was the first scientist to propose a sun-centered or heliocentric solar system where the fixed stars and the sun remain stationary as the Earth circles the sun. Because he did not observe the background stars shifting during the year, Aristarchus also theorized that the sphere of fixed stars is so far away that the distance between the Earth and sun is insignificant. It was this great distance, more than the Earth's motion, that caused other astronomers to reject his sun-centered model. For his understanding of moon phases and the rotation and revolution of the Earth, Aristarchus is our next amazing astronomer of antiquity.
Welcome to Athens, capital of ancient Greek culture and civilization. The Parthenon on top of the Acropolis faces east to capture the first light of the rising sun each day. Aristotle, our next honoree, came to Athens to attend Plato's School of Philosophy when he was 17 and became Plato's most favored pupil. His training focused on philosophical speculation rather than direct observation. Aristotle argued that the universe must be spherical and finite with the Earth at its center. Since he did not observe the stars moving, he concluded that the Earth cannot be moving and that the moving sun, moon, and planets must be circling a fixed Earth. Aristotle believed that each planet followed a path created by a certain number of heavenly spheres, a theory that required more and more spheres to explain the observed motions of each planet. Aristotle's spheres had a profound influence on medieval scholars who used them to interpret and support Christian theology. Unfortunately, Aristotle's assumed truths kept scientists from considering the simple and accurate experimental model of Aristarchus. Nevertheless, Aristotle was an amazing astronomer because his questions stimulated our quest to understand the structure of the universe, a quest that continues today.
Welcome to the ruins of Cyrene in eastern Libya. Eratosthenes, our fifth amazing astronomer, was born in Cyrene when it was an influential and wealthy Greek colony in North Africa. Founded over 2,500 years ago, Cyrene was one of the principal cities of ancient Greek culture. Its Temple of Zeus is the largest outside of Athens. He compared observations of sun shadows made at Alexandria with observations made at Aswan, the first cataract of the Nile River. Aswan is almost due south of Alexandria and is very close to the Tropic of Cancer. Eratosthenes knew that the sun is almost directly overhead at noon in Aswan on the summer solstice, the longest day of the year when the sun is highest in the sky. When the sun is straight up, vertical objects cast no shadow and the sun's light can reach the bottom of a vertical well. On the same day in Alexandria, the sun is not quite overhead at noon. Objects cast small shadows. Eratosthenes measured the angle of this shadow and realized that this angle was the angular distance between Alexandria and Aswan on a great circle of the Earth. Eratosthenes realized that the distance around the Earth was just over 50 times the distance from Aswan to Alexandria. In this manner, Eratosthenes makes a very accurate calculation for the circumference of the Earth. Eratosthenes also observed lunar eclipses and saw the shadow of the Earth on the moon. From this image, he determined the moon's diameter is about 1/4 of Earth's. For his measurement of the true sizes of the Earth and moon, Eratosthenes is our next amazing astronomer of antiquity.
Welcome to Naples, Italy, home of the National Archaeological Museum. Inside is a Greek sculpture of the god Atlas carrying a globe on his shoulder. It is not an Earth globe, but a globe of the star field. This very accurate celestial globe is probably based on the star map of Hipparchus, our next amazing astronomer. We can imagine this celestial globe all around us. The constellations mapped by Hipparchus cover all of the sky that could be seen from the Mediterranean. He cataloged all the zodiac patterns, the constellations near the North Pole, and many other patterns throughout the sky. Using the astrolabe he invented, Hipparchus produced the first accurate star map with over 850 stars, ranked on the brightness scale we still use today. The Hipparchus globe also shows the celestial equator, a great circle in the sky lying directly over the Earth's equator, as well as the zodiac path marking the sun's position each day of the year. The sun is at this intersection on the vernal equinox in March of each year. Over 2,000 years ago, a cargo ship sailing from Rhodes to Rome sank with its cargo of luxury items, and among the statues and vases was an incredible astronomical device called the Antikythera Mechanism. Crusted over by 2,000 years at the bottom of the sea, it is difficult to see the traces of gear wheels and written scales. X-rays show the remains of at least 30 interlocking wheels turned by a hand crank. On the front of the mechanism are two metal dials, one inside the other, showing the zodiac and the days of the year. Metal pointers indicate the positions of the sun, the moon, and the 5 planets visible to the naked eye on a given date. When the crank is turned, all the gears start to move. The moon dial makes 12 turns while the sun gear turns only once. Through a small window, another dial brings up the correct view of the moon. Separate dials display the position of each planet. The device could also have predicted solar and lunar eclipses. It's a mechanical wonder requiring a very detailed and accurate knowledge of motions in the solar system. This precision technology did not reappear until the mechanical clocks of medieval Europe. The accurate astronomy in this device is based on knowledge compiled by Hipparchus and taught to his followers on Rhodes. Hipparchus also calculated the distance to the moon and the length of the solar year to within 6.5 minutes. He was perhaps the greatest scientific astronomer of antiquity.
We return to the ancient Library of Alexandria to study the works of our final amazing astronomer, Claudius Ptolemy. Ptolemy lived in Alexandria during Imperial Rome, and he had access to the extensive works of the Royal Library. He relied heavily on the findings of Hipparchus and quoted him often. He also accepted Aristotle's Earth-centered universe without question. Ptolemy produced 2 major textbooks, an astrological text defining the Western zodiac with its 12 familiar constellations, and an astronomical text, the Almagest. The Almagest explained and predicted motions of the sun, moon, and planets based on an elaborate system of circles in an Earth-centered universe. Using his system, astronomers and astrologers alike could determine the positions of heavenly bodies far into the past or future. Of all the amazing astronomers, Ptolemy probably made the greatest impact on everyday Roman life. Leptis Magna in northern Africa is one of the best preserved cities of Imperial Rome. In their everyday lives, the citizens of Leptis Magna and most of Imperial Rome were probably more aware of Ptolemy's astrology than his astronomy. Affluent Romans incorporated astrology into every aspect of their lives, from religion to politics and daily affairs. Pompey, Mark Antony, and Octavian all used astrologers. Octavian, when he became the Emperor Augustus, had coins minted with the symbol of his moon sign, Capricorn. The Roman Emperor Septimus Severus was born in Leptis Magna and honored by this magnificent triumphal arch. He married the daughter of a Syrian priest. Soon, Syrian sun worship became the official religion of the empire, eventually displacing the Greek gods. When sun worship became the state religion, the emperor was identified with the sun, and astrology and astrological symbolism formed an integral part of government policy. The heavens were thought to control the earthly affairs of Imperial Rome. For collecting and synthesizing the astronomy and astrology knowledge, Claudius Ptolemy has perhaps played the greatest role in reaching the public and in preserving the discoveries of the amazing astronomers of antiquity.
7 astronomers and 7 amazing contributions. The Egyptian astronomers like Imhotep, who developed a solar calendar. The Phoenician Hanno, who sailed by the stars. Aristarchus, with his sun-centered solar system. The philosopher Aristotle. Eratosthenes, who measured the Earth's size. Hipparchus, with his eclipse tables and star maps. And the astronomy writings of Claudius Ptolemy. Their legacy would extend through the Dark Ages to the present. At the museum's George Observatory, visitors enjoy a beautiful starry night, almost as dark and clear as the heavens of antiquity, with star patterns and motions unchanged in thousands of years. Every day we use ancient astronomy, watching sunrises, sunsets, and moon phases, counting days, months, and years, predicting the seasons and eclipses, and gazing at the stars overhead, all a legacy of the amazing astronomers of antiquity